Hi, welcome again to magnetism. Here we have a bar magnet and the magnetic field line pattern is shown here. Note that the south pole has the direction of magnetic field line into it and the field lines come out of the north pole. Note that the field lines also go into the magnet. Okay. Another thing to note is that magnetic field lines are not lines of force. They do not indicate the direction of magnetic force on a charge. They do have the direction on the that the compass needle would point at each location. Okay. Now, why is that? We saw in the previous equation that the force on a moving charge depends on the velocity of it. Therefore, it also depends on the direction in which it is going, since velocity is a vector. Okay, so by just seeing the magnetic field line pattern, you cannot deduce the direction of force on a charge that's moving in the field. All you can say is what is the direction of the magnetic field, which is the tangent direction in at each point, and you can also say what is the relative magnitude of magnetic field by say looking at where they are actually nearer and where they are farther from each other. There are okay, farther from the poles they are farther away, so the magnetic field is weaker. Nearer the magnet, the field lines are closer together, therefore the field is stronger. Also note that the number of field lines is not a useful quantity. Why is that? Because we can draw as many field lines as we like. We can actually fill the space with field lines, because the field is spread over the entire space. I could draw also a field line here because there is a direction of magnetic field at each point in space. Okay, so I could draw as many field lines as I wanted, but again the field lines would be closer together here than here. So that's it maybe. Yeah, the like poles repel, as you know, and the unlike poles attract. So this is how magnets behave, the basic thing. And then we have the corkscrew rule as given in the NCERT, but let's call it just a right hand rule for magnetic fields due to a current element. What we do is that suppose current is going in this direction, we place our thumb aligned with the current direction, and then the direction in which our fingers curl is the direction of magnetic field lines. Okay, it is not, these curly things are not magnetic fields, but they are magnetic field lines. Remember that the magnetic field vector is a vector which is represented by an arrow like this, but these curly things represent the direction of magnetic field at each point. At this point, for example, it's the tangent like this. At this point, it's the tangent like this, and so on. Okay. So we can use this to see how two parallel current carrying conductors behave. Let's have an example in which the two wires parallel to each other carry current in the same direction. Then consider the field lines of this wire. We align our thumb in the direction of current, and then the field goes like this. So at this point it's coming out of the page, so the field at that point is out of the page, while the current is going in the plane of the page in this direction. Okay, so since current is in this direction, as we know, current is the taken as the direction opposite of the flow of electrons, that is, it is the taken as the flow of positive charge. So Yeah, by this we have the direction of force as the direction of v cross b, velocity of the positive charge cross b. Okay, actually here positive charge is not flowing and electrons are flowing, but let's assume that positive charge is flowing in this direction, in the direction of current. And so we have v cross b is out of the page, so we get like this. And oh wait, let's do it again. Current going in this direction, field like this, so b out of the page like this, and I like that. So I is the direction of positive charge. Then I cross B would be we place our hand in the I direction and then we curl our fingers towards the B direction, which is out of the page, and the force we get is like this in the plane. So actually it's attracted to this wire here. If we do that process again for the field line of this conductor, the field would be like this, and when it reaches this wire it would be actually going into the page, and the current is like that. So I cross B, that is the flow of positive charge cross B, V cross B would be in that direction. So this is pulled here, that is pulled there, therefore the two parallel conductors carrying current in the same direction attract each other. And if you do this thing for parallel conductors carrying current in opposite direction, you would see that they repel each other. And now we can use this knowledge to understand the deflection here. When no current was flowing, the north pole of the compass needle points towards geographic north, that is towards the Earth magnet's south pole, because opposite magnets opposite poles of a magnet of two magnets attract each other. Okay.